of my sons are born in February, so he wanted to have a birthday party with Grandma. So we had to go out of town. Okay, so annoyingly, I have left my notes at home, and I need to look up something right quick, otherwise I'm going to misstate it if I'm not careful. But I want to share with you guys is a theorem of Caratheodory. And, you know, full disclaimer, this is not all is done in Calculus 1. Like, the way I'm looking at things here is perhaps a little bit unusual. So the question is as follows, right? So we're about to derive some rules of calculus. Product rule, quotient rule, chain rule. And the question is, how should I do that? Now, one way I could do it would be just state the rules and don't prove anything, right? And that's an approach a lot of instructors take. Another approach would be to prove it in the way that we did before the test. So like on the test, remember you guys had the proof that the derivative of a sum is the sum of the derivatives, remember that? How did you prove that? Just directly from the, so this is on page 173 of my notes. So I'm just going to take a minute here to share it with you. Here it is. Let f be a function whose domain includes I, all right, and A is an element of I, all right. Then f is differentiable at x equals to A, all right, if and only if and only if there exists a function phi from I to the reals with the following two properties. One, phi is continuous at A. That's IFF. I'll explain in a second. Two, I'm on borrowed time here. My computer will, you got to understand, I got about 30 seconds before this goes black. But that is a very good question, and I should talk more about it. And if f of x minus f of a is equal to phi of x times x minus a for all x in I. So let me try to explain what this theorem is saying and why I think it's interesting. So IFF is if and only if. So like logically, what that means is that the expression before and after that is equivalent. Like I can either trade the statement f is differentiable at the point, or I could have the statement f has this function phi with these two properties. So the existence of a function phi in an interval I that matches up with a function like that, that's equivalent to differentiability. So this thing here, that's just a shorthand for if and only if. All right? And, if you want another shorthand for that, it's the double arrows. It's a biconditional statement. So let me home in here on that first equation here. And this right here, right? We could trade that for the following equation, right? This says that f of x is equal to f of a plus phi of x times x minus a. So does this remind you of anything? Like what did we have? Just a reminder, the linearization of a function at a has the following formula, right? It's f of a plus f prime of a times x minus a. The difference between the linearization of a function and the expansion of point 2 is that the coefficient of x minus a, it's not a number necessarily, it's actually it's a function, right? But the claim is that that's equivalent to saying the function's differentiable. Now, how do we prove such a thing? So it's an if and only if proof, right? So let's look at the forward direction of the proof. Let me close this door here. So we should assume f is differentiable at a, all right? Then what? I'm going to set phi of x equal to f of x minus f of a over x minus a for x not equal to a, right? Can I do that? I mean, I can do that, right? Now, if I want to prove this theorem, I now need to do what? I need to show that this function phi I'm making up, right? It has to satisfy what? Property 1 and property 2. So let's look at property 1. Why is phi continuous at a? Can you guys tell me? What's the limit as x goes to a of phi of x equal to? But if we said f is differentiable at a, right? So does that limit exist? I mean, this is the difference quotient, right? So by definition of differentiable, this exists and it's equal to f prime of a, right? So let phi of a equal to f prime of a, then phi is continuous at a, right? also, what else do we need? We need that this identity, the orange circled identity holds for this function phi that we're defining. So how about this here? We have what? We have f of x minus f of a equals to phi of x times x minus a for x not equal to a from star, right? Now, I need more than that for number 2, right? I also need what? And my proof, I'm assuming what, by the way, at the start of all this? I probably should have mentioned, we're assuming that I is a subset of the domain, A is a point in I, right? Like that. That's a precondition to this whole discussion, just like in the theorem. So from star, we have this, right? For x not equal to a. How about x equals to a? Is this equation true for x equals to a? What happens when we put in x equals to a here? Why is it true? If I put x equal to a here, I get 0 on the left-hand side. If I put x equals to a, I get 0 on the right-hand side. So, and we just said that phi of a is what? F prime of a, right? So 0 equals 0, check. Okay? So that is the forward part of the proof. So when we prove a biconditional, we have to prove this direction and also that direction, the converse direction. How about the other direction? We assume phi with 1 and 2 are given. What do we have to do? We have to prove what? F is differentiable. How do we prove F is differentiable? How about this? From 2, have that phi of x equals to f of x minus f of a over x minus a for x not equal to a, right? So claim, we're going to claim that f prime of a is equal to phi of a. So the limit as x goes to a of f of x minus f of a over x minus a is equal to what? Well, it's equal to the limit as x goes to a of phi of x, right? But what did we say? We're assuming 1 and 2 are given, right? What was 1? Phi is continuous at x equals to a, right? So if phi is continuous at x equal to a, this is equal to phi of a by 1. And that completes the proof because we said our claim was that f prime of a was phi of a. But we've just showed that the limit of the difference quotient is equal to phi of a, which goes to show you that the function is differentiable at a and that the value of the derivative is the value of this function phi at a. So, like, if you wanted to give a name for the phi, what is phi of x? Phi of x is really just it's the difference quotient function, or it's the average change function, right? Phi of x is equal to f of x minus f of a over x minus a. It's the change based at a function. That's what phi is. You say, well, I don't see how this really gets us anything. And okay, I mean, I maybe thought the same thing in myself at one point, but it actually makes proofs like a lot easier. See, because let me show you. Remember we proved that differentiable implies continuous. before test, and I showed you the argument, but it was kind of a pain, right? It involves some kind of sneaky steps. But now we can do it easier as follows. So here's theorem. F differentiable at x equals to a implies f continuous at a. So here's my proof. Assume f prime of a exists, then by theorem of Caratheodory, which I'll just say Cara, there exists phi, right? Function such that what? F of x equals to f of a plus phi of x times x minus a. Observe the limit as x goes to a of f of x is the limit as x goes to a of f of a plus phi of x times x minus a. But this is the limit as x goes to a of f of a plus the limit as x goes to a of phi of x times the limit as x goes to a of x minus a. This is a constant, right? Limit of a constant is just the constant. This exists, this is phi of a, right? Which from the proof of the theorem of Caratheodory, we know is actually f prime of a, right? For what it's worth, we know that that's actually f prime of a. What's the limit as x goes to a of x minus a? As x goes to a, x minus a goes to? I'm starting to be scared to grade that test. Come on, guys. Someone here knows this. Mm-hmm. A minus a, which is? I think I heard a 0, right? Yeah, 0. So if this is 0, and this is a number times 0, 0, what do we got? Just f of a. What does that prove? That proves that the limit of the function as x approaches a is equal to the value of the function a, which is to say that f is continuous at a. That proves that f is continuous at a. If you compare this proof with the one I gave you before, you'll find that this one is much easier. It's direct. See, the theorem of Caratheodory gives us a formula for a differentiable function that we can work with. I understand I'm going to lose some students' attention going through this proof here. Like, I know, it's kind of boring. But what it gives us is something really, really concrete to work with. And that's important because as we're discovering the product, the quotient, and the chain rule, we now have a very easy way to discover these rules for ourselves. Right? We can use the theorem of Caratheodory to discover the rules. So, great. Let's talk about product of functions, right? Let's talk about the product rule. See if we can discover it. So, assume f and g differentiable at x equals to a, right? What does that mean? That means that f of x is equal to f of a plus some function, let's say phi sub f of x times x minus a, right? And it also means that g of x can be written as g of a plus some function phi sub g of x times x minus a, using the theorem of Caratheodory. So what happens when we multiply the product of f of x times g of x? What do we get? So we have f of a plus phi f of x times x minus a, right? Times g of a plus phi g of x times x minus a. So you guys multiply that out for yourself. What do you get? Multiply that out. What do we get? We get f of a, g of a, right? And then plus, let's see here, phi f of x times g of a times x minus a. I'm going to put the x minus a terms last, okay? Plus f of a times phi g, x minus a, and then the phi f phi g, x minus a squared, right? So I could rewrite that as f of a, g of a, plus, let's see here, big parentheses, phi f of x, g of a, plus f of a, phi g of x, plus phi f, phi g, x minus a, all times x minus a. Let me give this thing a name. Let me just suggest that that's phi of x. I mean, if you want me to, I could say that's phi of fg of x. It's the phi function for the product of f and g. See, because what we have is we have fg of x, right, minus fg of a is equal to phi sub fg of x times x minus a. My claim to you is that this phi fg function satisfies properties 1 and 2 of the theorem of Caratheodory for the product function. What do we need for it to satisfy properties 1 and 2 for the theorem of Caratheodory? We need what? It needs to be continuous at A, right? And it also has to do what? It has to satisfy that equation. Equation 2. Does it satisfy equation 2? By construction, it satisfies equation 2. Because, so here fg is playing the role f did in the definition of the original statement of the theorem. So yeah, I mean, this is property 2. Is it continuous? What's the limit as x goes to a of phi fg of x equal to? So let's remember from the theorem, what did we learn? We learned that in the proof of the theorem, we learned that the value of the function phi at the point is the derivative, right? So the limit as x goes to a of phi of x is f prime of a. So this limit is rather fun to do. This guy limits to f prime of a, right? This guy limits to g prime of a. Over here, we have f prime of a, we've got g prime of a, and as we were just discussing, 0. So what happens, this piece goes to 0, this piece and that piece survive. What do we got? What's the limit equal to? Yeah, f prime of a times what? Times g of a plus f of a times g prime of a. So if we define well, I mean, that is what the f, and that is also equal to what? That's also equal to the fg of what? Of a, right? So anyway, my point is, it's continuous. It satisfies 1 and 2. That proves that the product of differentiable functions is what? Satisfies 1 and 2. So the product of differentiable functions is differentiable. But more interesting than that, we now know what its derivative is. Right? The derivative of f times g is f prime g plus f g prime. And that's the product rule. So there you go. Theorem. Fg prime is equal to f prime of a times g of a plus f of a times g prime of a. That is the product rule. Now, I think it's healthy, good, in fact, even better, to rewrite that as d dx of f times g is equal to df dx times g plus f times dg dx. There's what the product rule looks like in the differential notation. So, to recap, what we did was we took and assumed the functions were differentiable at a. That gave us the ability to write the function as its value plus the difference quotient function times x minus a by the theorem of Caratheodory for f and for g. Then what I did was I took f of x times g of x and I multiplied it out. I multiplied this times that. It gave me 4 terms, 3 of which I was able to factor an x minus a out of. I then had the insight to say, aha, whatever's there, that must be the phi function, quote unquote, for the product function, right? And in other words, this function, phi sub fg, satisfies properties 1 and 2 of the theorem of Caratheodory. And indeed it did, because we proved that the limit, first of all, it satisfies property 1, which I've now erased, sorry, because of that identity. And it satisfied property 2 because when we took the limit as x goes to a, well, all of these different pieces limit out like we'd like. Appealing to the proof of the theorem of Caratheodory, we know that the limit of f of x as x goes to a of phi sub f of x is f prime of a, right? This function, it limits back to the derivative at the point. And the same for the phi sub g, but derivative of g. And this other piece goes to 0. And so put it all together, this is a continuous function, that's its value. that proves that the product of two differentiable functions is differentiable. But more than that, it proves that the value of the derivative of two functions is given by this formula here. And this is what's known as the product rule. So that's what we did. And the product rule in differential notation I've written up here. d dx of f times g is df dx times g plus f times dg dx. Let me do a couple of examples before I go on. d dx of x times e to the x. All right. So here we do dx dx, e to the x plus x times d dx of e to the x, applying the product rule. And so what is that? That is e to the x plus x e to the x, right? How about d dx of sine squared x? So what that notation means is sine x times sine x, right? So product rule. What's the derivative of sine? Remember, we proved it was cosine. Cosine, yeah. So we get cosine sine, sine cosine. So the answer is 2 times sine x cosine x. Sure. Uh-huh.
Which x will it be at the product side?
Oh, sure. So I'm saying this is f, and this is g. So this is df dx g plus this is f, and then d dx of g. So it's that one.
No, what I meant is that when it goes to the equal sign, right?
Mm-hmm.
If that x now that was a number. Okay, let me come and show you. Can I see?
Sure.
So if this was a number, right?
Mm-hmm.
What will it have been right here? Is it this one or this one? That's what I meant.
This one or this one? I mean,
Okay.
this x is that x.
Oh, okay. That's what I.
Okay, okay. I mean, the derivative, one of the things I'm using is that we have this also, d dx of e to the x is e to the x. So, like, this gives me that e to the x, and that literally is the same x. I think that's what you're asking. Like, this x is this x, before and after. Okay. One more example here, d dx of, how about the square root of 16 x times the cosine of x. Oh, if I'm going to do just one more example, oh, fine, I'll keep it like that. All right. Fine. So the square root of 16x, we could do what? We could, that's really 4 times the square root of x, but yes. Right? So we have d dx of 4 times the square root of x, right? Times cosine x. So we can take that 4 and we can pull it out by properties of the derivative that we know from test 1, right? So we've got 4, yeah, d dx of the square root of x, whatever that is, times cosine of x, plus the square root of x times d dx of cosine x. Now what's the derivative of the square root function? Remember, it's 1 over 2 times the square root function. What's the derivative of cosine? Well, the derivative of cosine was not sine, but it was minus sine, right? So we have minus the square root of x sine of x. There you go. Because the derivative of cosine is minus sine. Mm-hmm.
For question 2, all right, so if this sine squared x, right?
Yeah.
So why is the derivative, you have derivative of sine x times sine x? Why wouldn't you just put it in front like you did the second one?
Like I did the second one.
Yeah.
Well, I mean, this would be the df dx g term, and this would be the f dg dx term.
Okay.
So it's this product rule. And then this would give me cosine sine, and this would give me sine cosine, but multiplication commutes, so I could just do 2 times sine cosine for the answer. Maybe we should do an application to a tangent line before I go on anything else. Can you find tangent line? Find equation of tangent line to, let's say here, ooh, not 0, that would be bad. I was about to try to do the tangent line at 0. Can you tell me why I shouldn't do the tangent line at 0 for this function, example 3? Yeah, it's going to blow up, right? Do we have division by square root of x? Like, put 0 into that, it's not good, right? It's because the square root function's not differentiable at 0, remember? Square root's got an endpoint at 0. It's kind of got a vertical tangent there. So let's do it like 1. 1 comma, what's the value of this function at 1? Well, it's 4 cosine 1. So I'm going to call this whole thing, let's say, h of x, okay? So find the tangent line to y equals h of x at that point, right? So it would be y equals to h of 1 plus h prime of 1 times x minus 1, right? now h of 1, plug in 1, like I said, it's 4 cosine 1 because I get square root of 16, which is 4. Cosine of 1 is 1, so 4 cosine 1 is my value of that function. And then what's h prime of 1? So this is h prime of x, right? So h prime of 1, I plug in 1. What's that going to be? Yeah, it's 4 times 1 over 2 cosine of 1 minus the sine of 1. That number, whatever it is, times x minus 1. There you go. That's the equation of the, set that equal to y, right? That's the equation of the tangent line to the function y equals h of x at 1. Because we figured out the derivative function in example 3. Right? So we can use that function to find the derivative at a point by evaluating the derivative function at 1. I don't know about you, but I am very, very happy we don't have to calculate the difference quotient directly for this thing, right? Can you imagine taking the limit of h of x minus h of a over x minus a for this thing? Oh, it would be truly horrible. But the thing is we don't need to, right? Because now we have the product rule to deal with such examples. Okay? So, what do you do after you learn to multiply? You divide, right? So that's up next. So what are we going to do? We're going to assume f and g differentiable at x equals to a. And we're also going to need g of a not equal to 0, okay? So then, once more, we have f of x equal to f of a plus phi sub f of x times x minus a, and g of x equals to what? G of a plus the quotient function phi sub g of x times x minus a. And what else do we know? Where limit as x goes to a of phi f of x is what? These are continuous functions, right? The phi sub f and phi sub g. What is their what's their limit? By the proof we did today, it's g prime of a for the g. It's f prime of a for the f, right? Now, let's look at f of x over g of x and see if we can discover what the rule for the derivative should be for this. We got what? We got f of a plus phi f of x times x minus a over g of a phi g of x times x minus a. You want to cancel out that stuff? Yeah, I do too. And I'm going to spend about 2 minutes on it. If I get it, I get it. If I don't, we're going to bail on this, okay? Like the proof of the quotient rule, if you look at my notes, it's kind of a pain. And the proof in the notes that you'll find, I have done from the limit definition. I also have a proof in the notes from the limit definition. Like the way I showed you how to prove the product rule today is not typically done. A lot of people use the argument which is in the notes. And that argument is based on adding 0 in a kind of sneaky way. And so you should look at it. Well, what's more important than the proofs here for you guys, of course, is like understanding what the rule says and being able to apply it. So honestly, understanding examples 1, 2, and 3 is more important than my proofs today, for sure, for you guys at the moment, right? But this is the chapter in your mathematical life where you see these things proved, so I owe it to you to do these things here. And also, that was a homework problem. I asked you to prove the product rule using like the Theorem of Carathéodory. It's a homework problem. I think it might actually been a bonus problem in like mission 5 or something. So I think I actually worked a problem for you there, but that's not in the notes. Okay, so I think you're right. I think maybe rationalization is the way to try here, so to speak. So like I'm going to see if I do g of a minus phi g of x times x minus a over the same, if that does something magical. I don't know, maybe. Because if I do that, what happens? I get f of a, g of a, minus f of a, phi g of x, times x minus a, plus phi f of x times x minus a times g of a, and then the minus phi f phi g x minus a squared divided by g of a squared phi g of x times x minus a. Oh, that's the thing, is this times that and this times that cancel, right? That's the whole point of multiplying by what we did. So all that survives from that is the minus phi g of x squared times x minus a squared term. So my time is limited today. If I fiddled around with this for another 15 minutes, I probably could get it. But what ends up happening is eventually you're able to argue that what dominates the derivative terms are actually like this piece and that piece. And if you look at that, you've got, when x goes to 0, this piece is going to f of a g prime of a with a minus, and this piece is going to f prime of a g of a with a plus, right? And the bottom is going to g of a squared. And this is not a proof, right? But it is in fact the case that this is the quotient rule. Quotient rule. So here it is. In prime notation, it looks like the following. F over g prime of a is f prime of a g of a minus g prime minus f of a g prime of a. So a minus goes with the derivative of the denominator, and then you divide by the denominator squared. In the differential notation, it looks like this. d dx of f over g equals to df dx times g minus f times dg dx divided by g squared. And there you go, that's the quotient rule. the product rule is over here, yeah. Yeah, there's a plus for the product rule, there's a minus corresponding to the, you know, so let me give you an example. Example 4, I suppose. If we have d dx of tangent, that's something we couldn't differentiate before, right? But now we can. So we're looking at d dx of what? Sine x over cosine x. See, that's a quotient, right? And if we use the quotient rule, we have d dx sine x, parentheses, cosine x, minus sine x, d dx cosine x, divided by cosine of x squared, or cosine squared x. Now, how's that work out? Derivative of sine is what? Yeah, so we have cosine times cosine, which is what? Cosine squared x. What's derivative of sine? I'm an idiot. Derivative of cosine? Negative sine. So minus minus gives me plus sine squared x over cosine squared x. Yeah, we got 1 over cosine of x, and you could write that 1 over cosine of x squared if you like. And what is that? One over cosine is called, this was like on page 1 of your test. Did you guys get stuck on that one? I had the problem on the test, like cosine times secant plus sine times cosecant, limit as x goes to 0. Did I get you guys on that one? Sorry about that. This is secant, right? This is secant of x squared. So we usually just write secant squared x. And this is one of those results that's important to remember. So we should know. We should remember d, I'll use theta this time, d theta of tangent theta is secant squared theta. It's one of those ones that's famous enough that we try to memorize it. But you can derive it, right? It's just the quotient rule. The derivation is just the quotient rule. Another one. So 5. How about this? We got stuck on this one before. I'll do it now, though. If I had d dx of hyperbolic cosine of x, this is not exactly a traditional quotient rule example, but I'm going to show you how we can use quotient rule to do this one. So that's d dx of what? That's 1/2 e to the x plus e to the minus x. That's the definition of hyperbolic cosine. So some of this is easy. We can pull the half out, d dx of e to the x, right? And then here's where I'm going to start to use the quotient rule. What is e to the minus x equal to? Yeah, 1 over e to the x. So we can use quotient rule, right? With the numerator function being 1 and the denominator function being e to the x. So the derivative of e to the x is e to the x. So I'm going to use the prime notation this time. 1 prime, actually I'm not going to because I hate it when students use the prime notation. Although, admittedly, the prime notation is less writing. Well, it depends on what you know. I mean, it's like anything else. Like, you know, a nail gun is fine if you're trained, you know what you're doing. But it could be very dangerous if you just, like, I would go to my 4-year-old and say, yeah, here's a nail gun. Go nuts. I would want to get far away from that. Well, what is the derivative of 1? This is 0, right? The derivative of e to the x is just e to the x again, right? So we have 1/2 e to the x plus 1/2 e to the x over e to the x squared. And I lost something, didn't I? Is the quotient rule this plus that? No, it is this minus that, right? So that's supposed to be a minus, right? So this is supposed to be a minus. And then, of course, this is actually what? This is actually that's e to the minus x again, right? And so if you look at that, that's 1/2 e to the x minus e to the minus x. And you may or may not know this, but by definition, that is hyperbolic sine of x. So what happened to the what? I factored it out. This one? It's here and here, so it becomes, I factored it out. Well, this e to the minus x came up because we have e to the x over... Oh, okay. This step? Well, if I multiply this back out, I get 1/2 e to the x, which is this, right? And then minus 1/2 e to the minus x, which is that. So that's the, you know, that is a somewhat non-standard application of the quotient rule. Another example, d dx of like, I don't know, x squared plus 3 over the square root of x minus 7. So we have d dx. Yeah, d dx of x squared plus 3 times the square root of x minus 7 minus x squared plus 3 times d dx of the square root of x minus 7. All divided by the square root of x minus 7 quantity squared. So again, the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. Now the derivative of the numerator here is just 2x. The derivative of the denominator is 1 over 2 times the square root of x. So there you go.